I'm Matthew Petroff. I'm a postdoc at the Harvard-Smithsonian Center for Astrophysics, where I generally work on cosmic microwave background instrumentation and related observational cosmology data analysis. However, today I'll be speaking on the development of accessible, aesthetically pleasing color sequences for data visualization. As an outline of this talk, I'll start off by discussing some pertinent terminology and giving an overview of human color vision and color vision deficiencies. Then I'll move on to perceptual distance calculations and use that to show the issues with existing color sequences. Next, I'll talk about generating accessible color sets using algorithmic constraints, followed by an aesthetic preference survey and the results of that used for modeling aesthetic preference. Finally, I'll show the results and discuss some best practices. So a few pertinent terms for use of color in data visualization are color map, color sequence, and color set. A color map is a continuous sequence of colors that is used for example gridded data visualization. An example of this is the VRIS default that has been in Matplotlib since version 2. Color sequence, however, is discrete. An example of this is the current category 10 default in Matplotlib. You start off when you're plotting a line plot or a scatter plot. The first item you plot is going to be the first color. The second item is going to be the second color, and so on. These are also sometimes known as color cycles because if you run out of colors, the plotting code will repeat from the first color, or as a more generic color palette. I'll use this term in this talk when I'm referring to a sequence where the order matters, and if the sequence does not matter, I'll use the term color set instead. From a physics perspective, human color vision is photometry via cone cells sensitive to long, medium, and short wavelengths. The spectral response is shown in the figure. Essentially, you take this spectral response and use it to integrate your incoming light. So if it's either a emissive spectrum or the combination of an illuminant spectrum and a reflectance spectrum. Human eyes also have rod cells that are used for low light vision, but these are not color sensitive, so they would not be discussed here. There are also lots of higher level functions, such as opponent color processes, that are beyond the scope of this talk, as are the biochemistry aspects of how the cone cells detect light. Now that I've talked about typical color vision, I'll get into color vision deficiencies. These are commonly known as color blindness, although it's somewhat of a misleading term, since most people with color vision deficiencies can see color. The most common kinds are anomalous trichromacy, which is the shift in the spectral response of one of the three cones. These are shown in the first row of this figure. Starting on the left, we have protanomaly, which is a red deficiency, deuteranomaly, which is a green deficiency, and trianomaly, which is a blue deficiency. These represent spectrums that correspond to different shifts in the spectral response. So if we look at the limits, if we start out with just a shift of no shift, that is obviously just typical color vision. But if you look at the other extreme where you shift the response all the way to match the response of the adjacent cone, you have dichromacy, which is the missing of one type of cone, which is shown in the bottom row. The left two columns are colloquially known as red-green color blindness, which is, again, a bit of a misleading term because it corresponds to multiple kinds of color vision deficiencies. And since it implies that the issues are just with red and green, although the issues are with colors that include red and green. So for example, with a red deficiency, those individuals have issues with between, for example, blue and purple. Next, I'll move on to perceptual distance and how we can use this to calculate accessibility. CAM02 UCS is a perceptually uniform color space. Essentially, it was designed such that you take two different pairs of colors and look at the sort of the perceptual difference between these colors. It should correspond to the same Euclidean distance in the color space. Next, we need to figure out how to simulate color vision deficiencies. So here I used a method of Machado et al. 2009, which is able to simulate anomalous trichromacy as sort of an extension of the Brettel et al. 1997 method. It creates a linear transform that you can apply to linear RGB colors to get simulated colors. So if we take the output of this simulation and apply the same sort of perceptual uniform color space distances, we can sort of calculate the approximate perceptual distance for the color vision deficiencies. Now, if we take this distance for all color pairs in the sequence, for all color vision deficiencies, we can define a metric for accessibility, min delta E CVD. I'll step through an example of this calculation for the category 10 default in Matplotlib, starting for typical color vision. We just plot one item in our plot. We'll use just one color, so there's nothing to confuse it with, so we have a perfect score as 100 to start with. We add the second color. Now we have one pair to look at, and that decreases the perceptual distance metric. Add a third color, and now we have 3 pairs to look at. And again, we just take the smallest number for this part of the matrix. And we continue for the rest of the colors, calculating a distance matrix with the diagonal mask, since we can't confuse one color with itself. So now we take this and start filling in our table. Here, these are perfectly reasonable colors for typical color vision. There's no real set level where, this point, it's just too bad, because it depends on things such as how big your points are and other things. But really, if you're below 10, it starts becoming problematic. However, if we take this and we repeat the calculation on the results of the color vision deficiency simulations, we see there's a different story. It's no longer acceptably high distances. So for deuter anomaly or green deficiencies, we see the first 3 colors are fine, but then we add the 4th color to the sequence, we plot a 4th item, and it's very similar to the 3rd color for the deficiency simulation, so it's no longer accessible. It's even worse for protoanomaly or red deficiencies, where 2 colors are fine, but once you add the 3rd color, it's problematic. And there's similar issues with blue deficiencies to these, although it's not as bad. Red to green deficiencies are by far the most common color vision deficiencies. Now we take these columns, we take the minimum of them, we get the final min delta E CVD metric. This is sort of the motivation behind the present work. Is I have a color vision deficiency, and I work in astrophysics where the Matplotlib defaults are commonly used. So I regularly come across papers where I have difficulty reading the figures because they plotted at least 3 items, and the green and the orange are very similar to me. This, of course, is not to pick on Matplotlib. The defaults in many other plotting packages are as bad or worse. But this is just sort of the motivation, since I work in a field where Python is commonly used. Before we go and generate accessible sequences, there are a few other considerations to take in mind. One is minimum contrast, because colors that are too light are difficult to see. So one thing you just go is to make it really dark, but then there's a problem with that too, because dark colors have increased perceptual weight. So you plot multiple items, you give additional emphasis to some of them. So there's sort of a trade-off there. There are some existing metrics for minimum contrast for text, such as the Web Content Accessibility Guidelines. But when you're just looking at the contrast between text and a white background, those limits are far too constraining, because once you plot several items, okay, your contrast with the background is fine, but you also need contrast between your various items. And there are also some other issues with the way that metric is calculated, though I won't get into that here. Another thing to keep in mind is grayscale compatibility, because believe it or not, people still print things, and sometimes they print them in black and white. So being able to read your plots in that case is good. There are also large e-paper tablets that are starting to become more common for reading academic papers, and since those have grayscale displays, again, grayscale compatibility is good. It also improves accessibility for monochromacy, which is complete color blindness. It's pretty rare. There are also multiple kinds, so there's some caveats to that. And again, there are the trade-offs with color accessibility, because once you start restricting which grayscale colors you can use, you limit your actual colors that are available for your sequence. And the last aspect has to do with color names. Names that are colors that are easier to name or easier to describe in textual descriptions, and easier to match from those descriptions back to the colors in your figure. This can sort of be with a color saliency term metric. High color saliency corresponds to colors that are easier to name. There's another aspect that is known as basic color terms. This was first presented in 1969 by Berlin and McKay. And these are essentially colors that are somewhat universal across languages. They're things like blue, red, green, opposed to things like teal or some other obscure colors that aren't so universal across languages. So if you stick to basic color terms and use distinct basic color terms, it avoids questions such as, which blue. You plot 2 different blues on your same plot, and now you describe it as blue. That leads to confusion. So you can sort of avoid this by trying to use distinct basic color terms. This does bias our results somewhat toward English, but since the basic color terms are somewhat universal, this bias is relatively small. Now we can start generating random accessible color sequences. The way we do this is we start with a random RGB starting color, and then we randomly pick another color and calculate our metrics, or min delta E CVD and min delta J, which has to do with grayscale or lightness difference. If the new color, the thresholds are good enough, we add it to our list. If not, we don't, and we just sort of repeat this process until we have the desired number of colors, or we run out of the 16.7 million colors in the RGB color space, at which point we just throw everything out and start over. So the bottom here, this shows some random examples from this process for 6, 8, and 10 color long color sets. These are I'll have larger constraints, so higher thresholds for the lower, for like 6 colors, for example, since we can enforce larger constraints without restricting our color space or accessible colors too much. However, we don't just want to just optimize for the metric, partially because aesthetics also matter. If your color sequence is ugly, no one's going to use it. So we want to avoid that. Also, human color vision is complicated, so our metric isn't perfect. The perceptual distance metric has error in it, as does the color vision deficiency simulations. So to account for aesthetic preference, I created a online user survey. So after presenting the survey participant with a introduction and directions, they were presented with 2 different random accessible color sets and asked to choose their preference. After choosing their preference, they were then presented with 4 possible orderings of their preferred color set and asked to choose their preferred ordering. So this survey ran for roughly 2 years, from December 2018 to December 2020. Over that time, I collected roughly 22,000 responses from 2,200 user sessions. So thank you to all those who participated. Now that the data are in hand, they need to be modeled. So for this, I turned to machine learning using artificial neural networks. We essentially have 2 distinct data sets, one for sets, one for sequences, so these are handled separately with a very similar architecture. However, for this analysis, there are a few issues to address. First of all, how do we handle color sets or sequences with variable length? We have data that are 6, 8, and 10 colors long, and ideally we'd be able to apply this metric to color sequences that are, say, 7 or 9 colors long as well. We also want to train a model that produces a numeric output score. However, we have binary pairwise survey responses, so we can't just run a regression directly. So that needs to be addressed. And finally, aesthetics is very subjective. Also, some of these color sets or sequences are similar to each other, so the data is inherently extremely noisy. So you want to be able to fully utilize the data at hand. To start off by addressing the first question, the way I constructed the neural network is to start off by finding an optimal encoding for the colors. So for this, you start off with a single input color and feed it to a set of dense, fully connected layers, and this sort of allows the network to learn an optimal encoding. Then we repeat this, copy and paste it for the remaining colors, so there are shared weights between all the sets of dense layers. And then we feed this into some separable 1D convolution layers that can handle different lengths of the input color set or sequence. And finally, we take the average of the outputs of the convolution to produce a single numeric output score. However, we still need to figure out how to train this network. So this is addressed by taking this entire network here and copying and pasting it again with shared weights. And we take the difference of the outputs of these 2 copies of the network for your setter sequence A and setter sequence B. And then that gives us a single output score we can then train with binary cross-entropy loss, addressing our second question. As for the third question of how to best utilize our limited data, I turn to bootstrap aggregation for this. This is sort of a technique where you take your data set and you randomly split it into training and test portions multiple times. For each division, you take the trained data, you use that to train your network, a separate copy of it, and then use the test data to check for overfitting. And then once you've done this a bunch of times, you take the outputs from all these models and average them for your final output. The network was simultaneously trained using the 6 and 8 color data. However, the 10 color data was set aside for model validation. Early on during the survey, I disabled the 10-color data responses from the survey to avoid diluting the data further. So there's significantly fewer responses for 10-color data, which is perfect for validation. So once the final model was trained, all the architecture was decided on, then I looked at the 10-color data, and that showed that since the accuracy was similar, that the model was able to generalize past 6 and 8 colors, and since also that it was not overfit. Now, one last thing we have to do is decide on a final metric before we can produce our final results. So for color sets, this is fairly straightforward. As I previously mentioned, color saliency, or how easy a color to name, is a good thing to have. So I checked this and to see if there's a correlation between this and the aesthetic model score. As there was no correlation that I found, I just multiplied these two scores to produce the final score and choose the optimal 6, 8, and 10 color sets. Then I needed to find the optimal ordering of these sets to determine the final sequences. There's a bit more complicated here because there are some accessibility aspects to consider for the ordering. Because if you only plot, 1 or 2 items, you're only using the first and second color in the sequence. So if we can have larger distances to more accessible colors at the beginning, this leads to more accessible plots in general. So I favored orderings with larger perceptual and lightness differences toward the beginning, as well as darker colors for the beginning to have additional contrast with the white background. The initial colors are also more important for aesthetics as well. So I ranked all the sequences with the aesthetic model and looked at the first color of the top ranked sequence, and then threw out any orderings where that color was not the first color. And similarly for basic color terms, if they were repeated earlier than necessary, those sequences were eliminated. Once this was done, I multiplied the aesthetic model score with the accessibility score for the remaining sequences and used this to determine the final ordering and thus the final results that are presented here. Unsurprisingly, these 6, 8, and 10 color long sequences look fairly similar because they were all generated using the same technique and ranked using the same metric. They all start with blue, orange, and then red, although they do differ a little bit after that. As I previously mentioned, we can use tighter constraints for accessibility when there are fewer colors. So the 6-color and 8-color sequences have better minimum color distance. However, all these are accessible and much better than present defaults. Before I wrap up, I want to discuss some best practices. The main point here is to not rely solely on color to convey information. So if you're making a scatter plot, use different marker shapes. You use circles and squares and triangles instead of just different colored circles. You're making a line plot, use dashed lines and dotted lines instead of just solid lines. And additionally, doing it in the plot is great, but if you just refer to the color in your figure caption, that is still an issue. So refer to the dashed blue line instead of just the blue line in your caption. And if possible, include a visual depiction of what you're describing in the caption, although I do understand that journalists generally don't allow that, and I have yet to get one of these into a published paper. They're just in the archive copies. One last point is on color maps, which is something I didn't really discuss here, but these should have lightness gradients because rainbow color maps such as jet and turbo are not accessible and should not be used, although there are other issues with those as well. And finally, as a good rule of thumb, you should preview your plots in grayscale. You preview them in grayscale and you can still read your plot. It's probably accessible, although there's some caveats such that red and black is a bad combination because of the lack of long wavelength sensitivity by protonopes, so that leads to poor contrast. So as an example, I'm going to convert this slide into a rather uninformative plot and then convert the plot into grayscale. Here we can see that the legend in the bottom right, we can still match it to the bullet points on the slide, and also the comments about blue circles and orange squares still make sense since they refer to both the shape as well as the color. So in conclusion, I've developed new color vision deficiency friendly color sequences. These were developed using algorithmically enforced accessibility constraints combined with a machine learning based aesthetic preference model. A preprint of the paper that describes all the work that went into this is on arXiv, and I'm in the process of trying to get it accepted into a peer-reviewed journal. All the code that was used for the analysis, as well as all the data, including the survey data and the copy-pastable hex triplets from the final results, are on GitHub, as well as some other potentially interesting tidbits, such as a pure NumPy implementation of the machine learning-based aesthetic preference model. And finally, a sort of an aspirational goal is I'd like to see accessible defaults in commonly used plotting codes. The fact is people use defaults often without thinking about it. So if we use better defaults, that's a effective way to get people to make more accessible plots. Thank you.
Thank you for this really interesting talk. The reminder to everybody to post your questions in track questions-room-204. We have a question from Brian McPhee. Is there a way to test out our own color sets using these tools? I've been doing this by hand on my own matplotlib style with a WCAG checker plugin, but automated tooling would make this much easier.
Right, so there are a few ways to do this. In Python, there's the color spacious package, which is what I use to do the all the calculations. You use that has the Machado et al. Method built in, so you can use that to look at things. It also has color distance calculations, so you can use that. That's sort of the way I did all the math for this this code. As for the other ways, I have a website, colorcyclepicker.mpetroff.net, that has a web interface that you can sort of copy and paste your colors into, and it does these calculations as well. That was sort of the first aspect before I got into this. Had the survey and this other random generation stuff. Is my first attempt was I opened an issue on Matplotlib back in 2017, and as part of that, I went and made this web-based picker, and with the hope that someone would go and use it to make a more accessible sequence. And once that didn't happen, I went and did it myself. So yeah, those are a few things. But the big thing, though, is if you preview in grayscale and you can read your plot, it's probably fine.
Gotcha. Yeah, maybe like let's say you made plots in 2014. Is there a way to like go look at those plots again, or like any tooling to see how accessible they are?
Not that I'm aware of, but I could be wrong. Though ideally you kept your plotting script so you can regenerate it, right?
Only if you stayed in academia. Sorry. Okay. The next question from Medican. Do you have a favorite personal sequence?
Well, the ones I generated here. I prefer the 6 and 10 color to the 8 color, but that's I tried to avoid biasing it too much, as I decided on the metrics, and then I didn't go back and tweak it to try to make it look better. I stuck with the metric and just tried to tweak things as far as to maintain accessibility. Some of the additional constraints that I discussed right before presenting the final results were things I added after the accessibility survey, but that was more like things like I went and printed out the colors, some of the colors on a grayscale printer, and decided that okay, some of these are hard to read. Let me increase the grayscale constraint to try to make that more accessible. But it wasn't anything like I think this looks ugly. Let me try to change things.
The next question from Omri. Does it work on sequences larger than 10 colors?
In theory, but I didn't do that. It becomes, the way I did the computation, it becomes somewhat difficult, certainly for the order, because essentially you generate every possible order and then rank for that score for every possible order. And once you get above 10, it's 10 factorial, and it starts getting computationally problematic. And that's part of the reason why I had to come up with a method that would produce a numeric score instead of just doing it on, you could do pairwise based ranking, but that just would be computationally infeasible even for 10 colors.
Gotcha. From Thomas, can MPL have a PR even if it is not the default yet?
Yeah, I was sort of trying to get this paper, accepted before doing that, but at this point, I don't think the results are going to change. It's more of another round of review and getting more changes to the write-up and not really the results.
Gotcha. From Kyle, have you examined the delta E values from the default Seaborn color set? It seems better than the Matplotlib default.
Yeah, there's an appendix in the paper that looks at the defaults in a whole bunch of different packages. Seaborn is not really any better, and I would say that there's the Seaborn colorblind sequence, which is actually not colorblind friendly. Yeah, no, I think the only package I'm aware of that actually has like a good default is R, but not ggplot.R. Just straight R has a reasonably good color sequence because they did think about color vision deficiencies when they created it a couple years ago.
Cool. From Scott, are there tools to convert naively generated images to an accessible interpretation?
I mean, there are the tools like in color spaces where you can apply these simulations and look at them. Although, I mean, there are some caveats. Simulations aren't perfect. They're based on fairly limited data. And also you can clip out of gamut. So that does skew things a bit. But that would be what I'd recommend is looking at using these tools. Although you should try to be careful with using ones that are floating around online because some of those are quite bad.